Let's get started. So going back to this motivation, the virtual memory, it is a little bit confusing, right? I know. So let me give you one specific example with some background information first. Virtual memory. With virtual memory, right? So the thing is, we want to execute many different programs on the computer. There are so many different programs to run on your computer, right? So for example, so on Windows machine or Linux, on the Windows machine, right, you can execute Task Manager. Then check out how many different programs are being executed at the same time. Check out this. So look at this. You can scroll it down, right? There are so many programs are running on this computer, right? Look at this. These many programs are running at the same time. How these different programs are managed, right, by operating system. Right? So computer scientist was thinking about that problem, right? So running many different programs on your computer, and their solution is the virtual memory technique. And virtual memory technique allows you to share main memory, right? So animation is this. So that is one. Virtual memory technique allows you to share main memory very efficient manner. So main memory is shared among many different programs. There are so many different programs, right? Hello World, MS Word, Windows, so many programs. And these programs are sharing main memory pretty efficient manner, because only requested pages. Only requested pages, right? We are talking about 40 by page. Only requested pages are going to be placed in main memory. Right? CPU is accessing, for example, virtual page number 0. Then hello world, right? Then that actual page is going to be placed in empty slot. So OS is doing that management. OS here, okay, there are 3 different empty slots, right? Here, 3 candidates you can place. Then OS decided to place first page into the top slot. Then your CPU keeps executing your program on virtual space. Then it is time to execute the code in the second page. And that page is not present in main memory. So operating system is making the decision. Okay, you have 2 empty slots to choose. Then OS makes the decision. Right? Okay, I'm going to place that into an empty slot. So again, if you are able to take a snapshot of the main memory, then main memory is populated with pages from many different programs. That is virtual memory technique. So in short, virtual memory technique is using main memory as a cache. Cache is what? Temporary storage. Temporary storage, right? Temporary storage of hard disk. The hard disk contains everything. Hard disk, right? SSD, solid state drive, or hard disk contains everything. Everything, right? Your program and data. And then only requested pages will be placed in main memory. So that allows efficient sharing of main memory. So still very confusing, right? So let me give you one very specific example. For example, you are writing very simple program, C program main. Here, integer A, B, C. Then you are assigning 1, 2, A plus B. So on. Then compiler compiles this code and generate binary, right? When compiler generate binary, compiler has a virtual space in mind. The binary, the final binary is laid out on virtual space. So for example, okay, let me write down actual binary. That is binary. Okay. Then so that code, right? So you need to read A and B, then do addition, then store into C, local variable, right? So first code is location 0. That is virtual space. Your final binary. Okay? Your final binary will be stored in here. I'm talking about your final binary. That binary stored in your hard disk. Okay. First, location. So not absolute location, right? So probably relative location. Anyway, so binary. You have LDR instruction, memory read instruction to read local variable. R0, probably R1. Okay, reading A. Read A. Second, read B. So another LDR instruction, R2 probably, 2 and R3. Then addition, add the instruction, right? R0 and R2, right? A and B. Then probably R4, okay? R0, R2. You are adding these two and store into R4. And finally, after addition, you have to store the result into the C. Okay? So store instruction as TR instruction. The final result R4 should be stored. R3, let me use R5. The location of local variable C. Then let's assume so that is located for 0, then location 4, this instruction 8, and C. Then let's assume the data 1 and 2 are stored here. 1 and 2 stored here. Let's assume that it's stored at 1,000 location. 1,004. Just an example. Just an example. So first instruction probably reading from 1,000, right? R1. R1 would contain 1,000. R3, 1,004. And then location, so that location of A, location of B, location of C. You see, so the final instruction, store instruction is updated. Store, right? 3 will be written after execution, right? After executing that code, then you execute. Okay. So that is final binary, right? Final binary. Then I deliberately use that number because it is 4K byte. This one 4K because we are using 4K byte page size. Right? So the start location of next 4K. 3 zeros, right? 3 zeros means what? Hex number, 3 zeros. Then 12 zeros, binary, 12 zeros, right? In binary. So next 4K byte. So from here, next 4K byte start. So assuming that now you want to execute that program that is stored in the hard disk. You want to execute that program, okay? Program actually. Okay? So program counter probably start from 0 in that program. Right? Then virtual address that is generated. 0 is generated. Okay. So now you need to read the first instruction. First instruction. LDR, addition, SDR. You need first instruction from memory, but memory does not have your binary yet. Everything is stored in hard disk. Okay. So what you have to do is, okay, the first page, first 4K byte page. Let me use this one page. This page should be placed in main memory, right? And that page can be placed anywhere here. Right? 4K byte, 4K byte, 4K byte, anywhere. And OS is making that decision. So probably this one is empty slot, this one empty, right? So OS decided to place this one to here, probably. Actual binary. Okay. Then physical address, right? Virtual address 0 is generated. Then somehow you need to have 7,000, right? Start from 7,000. You have to have 7,000 somehow. So from 7,000 actual LDR, addition, SDR, and so on. Right? First instruction will be supplied to CPU. So CPU execute. Okay. So are you guys with me? Okay. So then CPU incrementing program counter by 4 to 4, right? Right? So 4 is generated. Then same thing, right? So now that page is now present in main memory. You can access second instruction from that page. Okay, 7,004. 7,004. Then execute second LDR instruction. Program counter is automatically incremented by. Then 8, right? 8. Then you need to have 7,000, 7,008. The third instruction supplied to CPU. The point is this virtual address should be changed to this physical address somehow. Right? Because operating system is placing your binary into that page, into some physical location. Operating system should create that translation information, the table, that's called page table. Page table. So the virtual space, right? The virtual space. We are talking about that binary, this virtual binary. The first 4 4K byte 1. The data 1 and 2. Sorry here. Second, right? Second 2. So this one 4K byte. So this 4K byte, we call that virtual page number. First 4K byte. Second 4K byte virtual page number 1, and so on. And CPU is generating 32-bit virtual address. That means you are creating how bit space? 4 GB space. Then how many virtual pages you have? 4 GB divided by 4K. Then 1 million. Okay. 1 million minus 1. For last page. 1 million. Here million is 10, 24. So we have 1 million different virtual pages in this space. Okay. Then this page table should have mapping information. So that is why you should have 1 million different entries in page table. Okay. So first entry contains mapping information, translation information for first page, virtual page number 0, right? This one, VP number 0. Translation information for virtual page. In this particular example, address 0. Okay. The location in first virtual page number 0. First location, right? That is mapped to this one. Actually, this one is page number, right? This one. Physical page number 7. If you ignore last 12 bit, then this one, the remaining 20 bit. If you say physical address is also 30, doesn't have to be 30 bit, but for simplicity, let's assume it is also 30. So last 12 bit is specifying what the location. Last 12 bit is specifying location within that 40 byte. Everything is 3 zeros, then you are talking about first one. Then everything is 1. The 12 1, then you are talking about the last byte in this 40 byte. So 12 bit, last 12 bit is pinpointing the actual data or instruction. Okay. And then the upper 20 bit is physical address. That is called offset. Offset, right? Because within that page, right? Within that page, it is specifying which one do you want to access. Okay. And then the remaining upper 20 bit, that is called page number. The number. Okay. So that is physical page number. Or in short, physical page number. So again, in this particular example, so you are generating location address 0, virtual address, then somehow it should be translated to 7,000 to access first instruction. Right? So here, what information you should do? First entry. First entry contains the translation information. 0 should be 0. Let me write only 4 text numbers. So that is offset, virtual address 0, right? And then this one, the 20 bit. 12 bit is offset, virtual address. And then upper 20 bit is called physical page number, right? So virtual page number. VPN, virtual page number. So virtual page number 0. This entry is containing translation information for virtual page number 0. Then in that particular example, 0 to 7, what information you have? What number you should have? 7, right? 7. Only 7. So you don't have to store this offset. You don't have to store this offset. Only you don't have to store this offset. Only physical page number should be stored here. Then by looking at this table, by referencing this table, you know, right? Virtual address 0. You are indexing. You are searching this page table. Right? Then okay, this is the one translation information. You read the information, then hook up this physical address. Okay. So let me do some more, right? So now, so let me. If you are remembering computer architecture class, right? So instruction patch. LDR instruction R0, R1. The first instruction patch is taking a lot of time. Right? Instruction patch. You are patching first instruction from the location 0, right? So then it will take so many time because you have to look up this page table. Then somehow, physical address should be generated 7,000. Then you read the first instruction. That is instruction patch. You just read the instruction. Right? Then after that, so here virtual address to physical address translation. Then what instruction came in? Instruction coming. Then you can do decoding. Instruction decoding. CPU interpret your machine code. Right? Then execution. In execution, it is not doing anything, right? CPU is computing memory location, 100%. Then memory access stage. memory access stage, it turns out to be what? R1 contains 1000. We are assuming X 1000 because the data is located. Data is located 1000 first data. So you need to, so now virtual address, right? So now virtual address. So here address, right? Address location 0, if instruction patch. That is coming from program counter. But memory access, right? You are using CPU, okay, CPU instruction patch. This one for instruction patch. And you need another line for data access. Data access. Another address. That is also virtual address. This one is for data access. Okay. And that is coming from ALU. ALU, in that particular example, right? Load instruction R1, 0, and CPU will do addition to R1, so 1000. 1000 locate address will be coming out from CPU data access. So data access, virtual address, but the data is not present in main memory. That is still so 4 KB next 4 KB. So 1 and 2. That is in hard disk. So you have to place that page 4 KB page 2 will be used to. This one should be placed somewhere in main memory. And OS is making that decision. So let's assume OS decided to place second page here. So first page here, second page here. So you have 1 and 2 information. So then address translation. So 1000 should be somehow. We have one physical address, right? Somehow should be translated to virtual page number. Virtual page number. Virtual page number 1. Virtual page number 0. Virtual page number 1. Virtual page number 1. That address somehow should be changed to 5000. You have to have 5000 generated and supplied to your physical address. So for that, you need to, OS is creating this page table. Right? OS knows the mapping information because OS operating system is placing this page into here. OS knows, right? OS knows everything. So OS is going to place some information here, translation information, but unknown. Second, this one, second entry, virtual page number. This one is for second entry, is for virtual page number 1. Virtual page number 1. So what information you should have here? Virtual page number 0 is corresponding to virtual page number, physical page number 5. So you should have 5. Are you following me? It's okay. Okay. So if you look at this layout, right? Physical memory, the page information. Your program is stored in probably consecutive locations, right? Consecutive locations, but actually in main memory it is distributed, not contiguous location. First page here, First page located here, second page located here, third page somewhere, fourth page somewhere. It is distributed, dispersed. Right? But you are executing your program on this virtual space. You are simply generating this address. Virtual space is virtual space. Nothing here, right? No memory, right? Address simply generated. Then you see the problem. What problem, right? What problem? Right? Look at this instruction patch. Instruction patch is taking so much time, right? So much time, because you have to look up. You have to look up this page table first to get translation, page per page number. Okay. That is first memory access, right? Memory access number 1. Memory access. Instruction patch. In instruction patch, you need to look up page table. Okay. We don't want to access main memory because main memory is so slow. We want to, because that is why we have a cache inside, right? Why do you have a cache inside the processor? Because main memory is so slow. I don't want to access main memory as much as possible. That is, I want to create somewhere here, make the cache, some cache. So I want to place the instruction and data into the cache. And our hope is we can find instruction and data from the cache. But that is not a guarantee, right? Well, not guarantee, but very high chances of finding instruction and data. So the problem is for each instruction patch and each memory access, you have to look up page table first. So after getting information, you access main memory again to get actual instruction and actual data. So for instruction patch, for each instruction patch and for each memory access, you have to access main memory 2 times. That is intolerable, right? Too slow, simply. We don't want to access main memory. That is why we want to place very special hardware component. Very special hardware component called translation loop aside TLB. TLB translation, right? Translation loop buffer. Translation loop aside. So this guy is taking virtual address as an input and generate physical address. And somehow, right? It has, like cache, it has some numeric parameters, something like 32 entries or 64 entries, depending on processor, depending on vendor, CPU vendor. The number of entries vary depending on x86, RISC-V, MIPS, depending on CPUs. Right? They are making the decision how many entries you want to have. So TLB structure can be like a cache. It is like cache. What is cache in Korea? Cache, temporary storage. Temporarily, you want to store some information, right? Temporary. It is also temporary storage. That is why we call this sometimes cache. Why? Right? Because you want to place recently accessed translation information. You accessed recently and that entry just now, right? So I want to place these 2 guys into here. I want to place these 2 guys here, somewhere in this TLB. Okay. Then TLB is able to provide physical address immediately without referring to this page name. If you have TLB hit, TLB miss. If you hit TLB hit, it means if you TLB has a translation information. If TLB has that information, here we can provide hitchcockage directly without looking up this stage table. So at the beginning, right? At the beginning, if you turn on your computer, TLB does not have anything. Nothing. Cache, right? We have a cache also. Cache is used to store your code, instruction, and data. That is your program, right? Turn on your computer. Cache does not have anything. Nothing is some junk information, trash information here at the beginning. So at the beginning, obviously you have TLBs. TLB does not have translation information. So then no choice, right? You have to access page table. Then provide that information, store that information here. Then afterwards, very likely to have TLB hit. Because why? This is a page-based translation information. Page is big, 4K byte, right? So instruction cache, for example, you are accessing first instruction, location 0. Then at the beginning, TLB miss, you don't have, right, translation. Right? So you place that byte into here somewhere, let's say 7 here. 7. Then instruction is provided and CPU executes first instruction. The program counter is changed to 4. Then 4. Right? Then location 4 is within first virtual page. So inside this virtual page, right, you can have 1024 instructions, ARM instructions. Right? So next instruction is very likely to be within that page. That means it has very good locality. Special locality. What is special locality? If you access one memory location, very likely to access its neighbor. 04 neighbor, right? 048 neighbor, right? So because translation information is per page basis, first time you miss, but next time very likely to hit. Hit rate is very high. Okay, any questions so far? There is almost everything. It is very basic, high level, and high level mechanism. Any questions so far? So again, your application, right? Your application is monopolized virtual space, right? Every time you access your program, your application program is fully utilizing this virtual space. This virtual space, 4 gigabyte virtual space, is used by only your program at some point in time. Okay, 1 millisecond, right? Let's say every 1 millisecond, OS is invoked, task scheduler is invoked, then execute a different program. Right? So here, hello world, and sorting program. Right? Next 1 millisecond. First 1 millisecond, right? Hello world is monopolizing this full, clean, white. Nobody using virtual space, but hello world. Then context switch. OS decided to execute the sorting program. And sorting program is fully occupying CPU and its virtual space. Okay. Then there should be separate page table for hello world, right? And separate page table for sorting program, and separate page table for another program. This one is for that addition, page table for addition program. And you need to have another. So let me, so So main memory still, main memory. Another page table. This one is for that addition. First program. This one is sorting. For sorting, program page table. So context switch. Then next time you execute task number 3, task number 1, task number 2, task number 3. You need to have separate page table, translation table. So every time you do context switch, then you should know the location of page table. You need to know the base location. OS is going to place page table in memory. OS will place this page table in memory. Here, this page table in memory. Then you need to know the start location. Right? To look up this page table, right? You need to know start location. The start location is recorded in system register. Inside the processor, there is processor. CPU 4, then including PLB and cache, that is processor. For example, Core i7, Intel Core i7, or ARM, Cortex A9, Cortex A9. So we are using Cortex A9. Cortex A9 has CPU 4, PLB, and cache. So, and inside the processor, you have very special system register for. In case of ARM, translation table base register, TTBR. So every time you do context switch, TTBR should be reprogrammed, changed, updated. Okay? First time, it is pointing that location. Okay? You do context switch, then execute task 2, then you have to reprogram. You have to update TTBR so that it can point start location of this page table. And then you do context switch. Context switch T3, T2, T3. Then that should be updated to point that location. Okay. And page table lookup. Page table lookup is based on what do you think? You need to look up the page table, right? And how do you search? Which entry you have to check all these virtual tests, especially virtual tests. Because that contains page number, only page number. Again, the first entry, first one is for virtual page number 2. Second, virtual page number 1. The last one, virtual page number 1 million. 1 million. You have 1 million virtual pages. Okay. So in indexing, right? Which entry you have to look up? Indexing. Which entry you have to look up is determined by virtual page number. Virtual page number. Virtual address. Then you ignore last 12 bit. So that is the offset, and upper 20 bit is virtual page number. So you need to know virtual page number from this location. TTBR is pointing the base location, start location. So from here, you search specific information. For virtual page number 0, then you read. And then there is a one. So page table lookup is performed based on TTBR and virtual page number. Virtual page number is providing offset. From here, how many word or byte, depending on the size of each entry. Typically, each entry is 4 bytes. Also depending on CPU, but in ARM Cortex A9, each entry is 4 bytes. 4 byte, 4 by 4 by. That means this table can be as big as you have 1 million entries, 4 megabyte. Page table size, 4 megabyte. Each entry 4 byte. Then again, using this virtual page number, you search each entry. You have to. Okay, that is the one. Then let's move on to I think we did okay. This one. 산호? Yes. So I want to talk about this virtual address size, okay, and physical address. How wide this virtual address and physical address would be. So virtual address with this 32-bit, right? I told you 32-bit. That is typically determined by CPU architecture. 32-bit CPU. 32-bit CPU. The meaning is the basic unit of data processing. It has ALU. It is taking two 32-bit data and doing some operation, generate 32-bit output. And program counter is also 32-bit. Register 5, R02, R15. Each register is 32-bit in size. Right? Equal program counter. So address, right? To instruction fetch, the PC information is going out. So naturally, that is equal to bits of program counter, size of program counter. So 32-bit. Okay. But in case of 64-bit architecture, I told you, right? 64-bit architecture, if program counter is 64-bit, it is creating 2-bit space, 16 exabyte, virtual space. That is way too big. So CPU vendor decided to reduce it to 48 bit. In case of 64-bit architecture, 64-bit x86. The same thing goes to ARM. So your smartphone, 8 ARM CPUs, 64-bit ARM CPUs. Okay. So the thing is, this virtual address size is typically determined by CPU architecture, but not necessarily equal to the architecture size. 32-bit architecture, 32-bit. 64-bit architecture, they use 48-bit. It is not necessarily the same. How about physical address? Physical address size. The physical address size. The physical address size determines what? How big memory you can install on your computer. That is determining the limit of your actual main memory. Physical address size is not necessarily same as virtual address. It typically depends on market segment. So, for example, the Intel is producing CPU for that desktop PC, personal computer. Generally used, right? Everyone is using personal computer, right? And also they are producing server computer. Server that is used in a data center. In desktop computer, typically we don't need that much that big main memory, right? than big memory. So that means, look at this, pin out. Look at this. So on the back side of this chip, there are a lot of pins, right? Physical pin out, right? So some of them are, physical address. Some of them are data line. So memory, these days we are using DIMM, dual inline memory module, right? Physical address and some pins are data line, data bus. So that is typically 64-bit. So 64-bit and some other information, some connections, some control information. So read transaction, write transaction. What do you want to do? Right? You want to read from memory? Okay. So address, data, and some control information. Those are necessary, mandatory signals you should have. You should inform, okay, I want to read from memory. Sometimes I want to update memory, right? Read or write, something like that. Right? So, okay, so pin, okay, a pin. So that pin, so many pins coming out from the chip, okay. Then desktop, computer. Desktop computer, you don't have to provide, very wide address line, because that is, this pin is directly related to price of the chip. How expensive, right? There is $100, $200, $300, right? That is directly, if you increase the pin, then it's going to be more expensive. So you don't want to have very wide physical address for desktop computer. Right? But for server computer, you need to install your big memory, right? That means you need to provide, Intel should provide much wider, not much, but wider address. Okay? So sometimes this physical address, 32-bit architecture, Intel used to provide 36 physical address. This one is more wider, 32-bit architecture. It means you can install up to 64 gigabytes, 2 to the power of 36. 64 gigabytes, power of 64, right? 64. And 64-bit architecture, virtual address, 48-bit. Then physical address. Do you remember the message I showed? My expression. 39 or 42. Physical address. Something like that. So so again, so these two are not supposed to be the same. So depending on market segment, they are providing different width of the address. Okay, so that's why I do this. 32-bit virtual address, then physical address. In this case, 30-bit. Okay, so move on to. So let's read this. Then I think we can simply read and move on. Better is that. Okay. 번호? Okay, wait, hold on. Battery is dead, so my student, changing battery. But any questions so far? Oh. Okay, so OS, let's read this together. OS, operating system, is creating page table. OS knows, right? It's mapping translation information. OS is creating page table for each program. Each program, right? Sorting program, page table, hello world program, sorting table, and so on, right? So page table information, page table contains translation information that is essential. It contains page code page number. Only page code page number and some miscellaneous information, some attribute. We are going to talk about that probably next week with a specific example, Cortex A9 example. Something like that, right? For example, this page is only readable. This page is read and write. Sometimes you read, sometimes you can write. Right? And some page, this page is executable. What do you mean by executable? You can read instruction from this page. There's a meaning. Executable. Reading instruction, meaning CPU is reading instruction. What is the intention? You want to execute it. Right? So executable. Right? So you can specify some attribute that is used to protect the page. Think about that. Some bad hacker, right? Some malicious, some bad people. It is marked as a read-only page. Read-only page. Some hacker is trying to update this page, right? Then what would happen? Some hacker will send it to your computer, and this page is marked as read-only. But hacker is trying to write some data. Then what would happen? Yeah. Two important events in computer, right? So we spend a lot of time, right? What event? Interrupt, there is interrupt, close. Exception, right? Exception will be generated. We haven't talked about the exception. We talked about undefined instruction. Right? And another example of exception is data overt. If you remember the page, vector table information, offset 0, reset vector, IVT, interrupt vector table, ARM vector table. And 04, software interrupt. 08 is overt vector for data overt. So if that attempt occurs, then exception will be generated. That means CPU will change program counter to 08, then jump to that exception handler. Okay? So you have to prepare that exception handler. You are doing everything. There is no magic. Some people is preparing that exception handler. So okay, so there is one virtual translation information. Then PTE, page table entry. Each one is page table entries. Right? PTE is indexed by virtual page number. Third bullet. PTE is indexed by virtual page number. Right? Which one? From this start location, which one do you have to access? Right? That indexing. Virtual page number. And the location, start location is in some system register. In Intel case, you have control register 3. Intel. Right? So every CPU has a special system register. It's special system register. Okay? That system register should contain the start location of page table. PTBR, Intel control register 3, RISC-V, SATP register. Supervisor address translation, and protection register. So every CPU has that special register, system register. Okay, C1. Okay, so some graphical representation. So you have virtual address. Virtual address is coming out from CPU. Okay, CPU. Then green is main memory. This one main memory. And page table is also located in main memory. Okay. And then that special register, PTBR, is pointing the start location. Then using this virtual page number, you look up this page table and read the specific page table entry. So then physical page number is going to come out, and that is concatenated. That is attached to this offset. That is physical page. Okay. Then using this physical address, you access actual. So why you need to have translation proof of side? This special hardware to efficiently support virtual memory. Without TLB, you have to access main memory 2 times. Every time you do instruction fetch and memory access. First access, page table lookup. Second access, actual instruction access, read, and or data mode. So first access, page table access. Second, actual data instruction. So that will slow down your computer too much. So that is why we need special hardware. It is special cache only for this page table. TLB is a special cache only for page table. It is holding only recently accessed page table entries. So the picture. Okay. You have virtual address generated from CPU. Then a TLB is inside the module called memory management MMU. You have to probably remember this MMU. MMU is used or not. Sometimes memory management some hardware. So TLB is searching with that virtual address. Then if you have a TLB hit, the translation information is found. Then here MMU can provide physical address. So based on that, you read an instruction data. And again, TLB is a special cache for page table. You are caching only recently accessed page table entries. Okay. So one picture, the whole picture now. We have cache, TLB, and cache. CPU, everything inside the processing, whole picture, right? So TLB is cache for page table. Cache is cache for instruction and data. So there is one example of processor block diagram. You have TLB, and physical address, and you have cache. So at the end, in this case, this is just an example. It doesn't have to be cache. Doesn't have to be accessed. with physical address. Sometimes cache is accessed with virtual address. If you remember the cache lecture, cortex A9, instruction cache is accessed with virtual address. So this is one example. Okay. So in this case, cache is accessed with physical address. Again, TLB is cache for page table. Cache is cache for instruction. So let's take a look at TLB structure. How do you structure it? We assume your virtual address 32-bit and physical address 30. Okay, this one. Minji. Okay. 홍주. Okay, so TLB structure, 3 kinds of structure. It is like cache, right? Direct map TLB. The other extreme, fully associated TLB. And in the middle, set associated TLB. Direct map, fully associated, and set associated. So this one is an example. You have only 8 entries in this case. 1, 2, 3, 4, 5, 6, 7, 8. 8 entries. So TLB contains physical page number, right? Because it should hold this physical page number. Then how do you access TLB? We have 8 entries TLB. From this address, we don't use this offset 12-bit because that's page offset. Page offset. Within that page, which one do you want to access, right? So we don't use last 12-bit. Then next 3-bit will be used to index the TLB. That's virtual page number. Then 3-bit will be used to search the TLB. Because we have 8 entries. We have 8 entries. You need 3 bits to select. In direct map TLB, right? Direct map TLB, we can use the same terminology. You have 8 different sets, right? So set number 0 to set number 7. So direct map TLB. In direct map TLB, you have one entry, one TLB entry in specific set. That is direct map TLB. Fully associated TLB, you have only one set. Fully associated, you have 8 TLB entries. You have only one set. Set number 2. Only that set is selected all the time. Everything is selected for lookup, like cache. Right? So if you select this one, then tag information is coming out. Very similar to cache. Actually same. Right? Tag information is coming out, and then the remaining address is compared against the tag information. So here you have a virtual page related, right? This is a virtual page number. 20-bit is virtual page number. And upper 17-bit is stored in tag. Right? So there is some of virtual page number information. Some, because only 17-bit in this case. 17-bit. So that is compared against that virtual page number, that 17-bit. Equal, then that entity is valid, then we call that TLB. So then that is the physical. In case of TLB hit, this is the physical page number. UED, that is coming out. Then that 12-bit offset is concatenated, attached to the physical page number. That is final physical bits. Then how about four-way set associated TLB? Four-way. Okay. Assume that you have 128 entries. So way number 0, 1, 2, 3. Okay. Way number 0, 1, 2, 3. So each way has 32. You divide 128 by 4. 128 by 4, that's 32. So each way contains 32 entries. Way 0 has 32 entries. Way 1 has 32 entries, 32, 32. So 128 entries. Okay. Then how do you search? Same, right? Last 12 bit, we are not using last 12 bit because that is page offset. Within that page, which one you use? And you have 32 sets. 32 sets. So you can use 5 bit. 5 bit from virtual page number. Okay. The remaining 20 bit is virtual page number. From here, you use 5 bit to select particular set. Then within that set, within that top set, you have 4 also elements, right? 4 entries, right? TLB entries. So then tag information is coming out at the same time. Hardware, right? All the information is coming out. Then that is compared against the remaining virtual page number. And one of the way matches. Then we call that goal hit. Right? We call that cache hit. TLB. Then actual physical page number is coming out from each way, and you go through this multiplexer. Multiplexer is selecting a 4-to-1 multiplexer. Select one guy out of 4. So then the hit information should be somehow provided to selection, multiplexer selection. Then that information, physical page number. So that is physical page number. Physical page number, then that is attached. Offset is attached to the physical page number. Okay, any questions so far? Here, Mr. Yes. Why do you want to check that? Excellent question. Excellent question. Really super excellent question. Yes, that is why we have a special field called address space ID. ASID. It does not show 해창's question is what? 해창's question is you have different page tables, right? Task 1, task 2. Each task is using this whole space, right? And by looking at this TLB does not have process information, right? Task 1, task 2, which process you are executing, right? Then we have some problem, right? You have to differentiate. Okay, that somehow you have to tell. Okay, that entry is caching that PTE for task 1, and probably way number 1 is containing PTE in task 2. It's supposed to have some process information, task information. Otherwise, right? Because each one is monopolizing this whole thing. So that is why there is a special field called address space. Right? This is address space, right? For address space, virtual space. Address space ID. Each process, each task is assigned with unique ID, unique space ID. Okay, task 1. Okay, so you have Task 1, you use ID task 1, right? You use ID number 10. I don't know what you know. This one is for task 1. Task 2, okay, task ASID, you 11. Task 3, okay, 20. You assign unique ID. By looking at this unique ID, you know which address space, which process you are accepting. It doesn't have, you know, I think I have something. Have here. Not here. This ASID address space. There is PLD. Then in addition to this PLD, you have ASID, address space ID. So ASID should be compared, right? ASID register should be also compared. There is also special register. When you do context switch from task 1 to task 2, right? Now ID, right? Your ID is 11. Then context ID in that case should be changed to 11. That is should be compared. So you know, right? If you don't support ASID, then what should happen? If you don't have ASID, assume that you don't have address space. This virtual address space ID. Then every time you do context switch, you have to flush. You have to invalidate everything in here. Flush out. That would be, you know, inefficient, right? So we want to keep recently accessed that information to TLD, because you never know, right? You context switch, then in the near future you execute, you know, the one you just invalidated. That is inefficient. That is why, you know, the CPU processor has ISID. Yes, super excellent your question. Okay, that is the one. Okay, okay, TLB structure. Because we don't have time, so let me quickly go through these two. Some important terminologies you need to know. TLB miss and page fault. TLB miss and page fault. These two are very important terminologies. You have to know. TLB miss. First one, simple TLB miss means TLB does not have, in both cases, TLB miss and page table, TLB does not have translation information. You have a miss. Simple TLB miss, first one. TLB miss and page fault. This hardware does not have translation information. And what is the difference between these two? Simple TLB miss means the page you are looking for, the one for example, this page you are looking for, that is already loaded in main memory. That is present in main memory. I'm talking about first one, TLB miss. Simple TLB miss. TLB miss, the page is placed in main memory, and TLB simply does not have translation information. In that case, what you have to do is you just place that entry into TLB. That is a relatively simple process. Simply read corresponding page table entry and place into TLB. Then you can read. You can access. And what is page fault? Page fault, you don't have you don't have the page in main memory. You are accessing, you want to access some page, but that page is not in main memory. That is called page fault. And that is resolving that issue problem is taking a lot of time because you have to access hard disk and place into. That is taking something like a millisecond. It takes huge amount of time. That is very severe problem. That is called page fault. So in case of page fault, what you have to do is place requested page from hard disk to some empty slot. Then also update here with translation information. Two things should happen. Then okay. Okay, let me quickly. In case of TLB miss, how do you resolve the TLB miss? TLB miss is that main memory has the page you requested, but TLB does not have the translation information. That means you need to look up page table and place translation information to TLB. And that process can be done either by software or hardware or both. Typically, CPU is providing option. Okay, you can do it by software or hardware. I'm going to do that automatically for you, hardware. What do you mean by that? Automatically done that by hardware. So TTBR is pointing that location, right? And using virtual address, CPU hardware knows with simple hardware, logic, okay. Hardware can find the location in page table, and hardware find out the location and read and place into TLB. So hardware is provided, right? CPU is provided, processor is providing the mechanism. Typically, Intel is providing the mechanism. Cortex A9 you are using, that is providing hardware based. We call that page table walk. You are walking this page table and find out the entry you need, and that place into here. In this case, we have one page table, but in reality, in commercial processor, Intel, you need more than one table. Two tables, 3 or 4 tables for translation. We can talk about that later on next time. But if you have to look up 3 page tables, page table number 0, 1, and 2. This one is for one program on let's say your Hello World program. So then this one is talking about, okay, you need to look up this one, and then this guy said, okay, you need to look up this one. Finally, the guy is translation information. So it looks like page table walk, right? Page table. You are walking this page table, find out second table, then walk page table, second one, then finally. This one is called page table walk. Page table walk. So again, the page table walk can be done by hardware automatically or software, but we use typically hardware-based page table walk. Okay, time is up. I think we stop here and continue next time. Okay, see you. One. Oh. 이건 페이지 테이블을 구하는 게 아니라 페이지별로 이제 액세스를 이제 스티브가 액세스를 할 거 아니야. 어떤 페이지. 근데 그 페이지를 액세스할 수 있는 충분한 권한이 있는지 권한이
권한도 있고 퍼미션. 다소 같은 거 퍼미션이라고 합니다. 리드온이나 혹은 리드라이트에는 퍼미션이라고 할 수 있고, 권한은 우리가 네가 충분한, 네가 슈퍼유저야? 혹은 유저야? 그럼 충분한 슈퍼유저만, 모두 슈퍼유저만 할 수 있는 건데 그런 권한. 그런 것도 명시할 수 있어요. 또 다른 것도 이제 명시할 수가 있어요. 이건 CPU에 따라 달라. 그런 것도 그거는 이제 CPU 스페시픽한 내용이기 때문에 인텔 CPU도 봐야 되고, 혹은 뭐 아무도 봐야 되고. 8번. 캐시. 오케이.
이거를 그러니까 그 스위치 연동 그래가지고 enable, disable 하잖아요. 그러면 그 두 개 enable 할 때나 disable 둘 다 할 때 어쨌든 토글을 시켜야 되는 거야. disable 할 때만 토글 시켜야 되는 거야.
뭘 토글? 그러니까 LED는 계속 뭐 토글이 되고 있어.
그런 걸 마지막 문장 조금 헷갈려가지고.
그러니까 캐시가 디세이블 돼 있을 때 LED는 1초 인터벌로 꺼졌다가 켜졌다가 켜졌다가를 1초 인터벌로 하고 있어. 근데 그거는 캐시가 디세이블 됐을 때.
그러니까 이거를 그러면 프라이빗 타이머를 써서 1초를 정확하게 재야 되는 건 아닌 거죠?
그럴 필요는 없죠. 그럴 필요는 없고 그냥 포문으로 하는 게, 왜냐면 그게 그거지. 그게 인텐션이죠 오히려.
네, 그렇죠.
타이머로 하면은 캐시하고 영향이 없었잖아. 그러니까 포문으로 해야 그 소프트웨어가 캐시로 쏙 들어갔을 때 굉장히 빨리 포문이 돌 테니까.
네.
그런.
감사합니다.
말씀하신 CR3 TBR 그러면 레지스터 사이즈가 만약에 메모리 피지컬 어드레스가 36비트다. 비트 괜찮겠네요.
이거 피지컬 어드레스 36비트면
TBR이나 CR3의 크기가 레지스터의 사이즈가 일반적인 레지스터랑 다른데.
그럴 수도 있지. 그럴 수도 있는데 지금 보면 36bit이라고 하면 우리 따져볼 수가 있는데 36bit 중에 아래 12bit은 안 쓰죠. 그러니까 지금 24bit만 여기 저장이 되면 되는 거죠.
그러니까 이거는 아키텍처에 따라. 그러니까 아키텍트가 정확히
레지스터의 크기는 그렇긴 한데 보통은 32bit CPU에서는 거의 모든 레지스터가 32bit이고 64bit에서는 거의 모든 레지스터가 64bit. 네. 34bit 이상은 그때는. 근데 어쨌든 만약에 이 32bit으로 모자란다라고 하면 32bit 아키텍처에서는 또 하나의 옵션이 있습니다. 두 번째. 그래서 요거와 요걸 사용해서 같이 할 수 있게. 그런 식으로 제공을 하죠. 만약에 더 많은 비트가 필요하다면.
그리고 한 가지 저희 제드보드에서 그러면 페이지 테이블 OS가 없다는 생각이 있어요.
그러니까 이렇게 여기 보면 실험 그 예제 코드가 여기 있으니까 요거 MMU 요거 예제 코드거든. 하나 보여주면 우리가 만드는 거야. 그러니까 페이지 테이블을 OS가 없지만 OS가 없으니까 우리가 만들어야지. 없지만이 아니라 그렇지. 예를 들면 이렇게 했는데 만들어 놓을게. 아직 안 만들어 놓은 것 같은데 내가 그거 오픈을 해보고
제가
확인해서 똑같이 프로젝트 만들면 거기 페이지 탭을 만들어 놓은 게 있거든. 그거 한번 확인해 봐.
TAB가 캐시랑 비슷하다고 해가지고 질문이 있는데요. 부트업일 때 이제 예를 들어 처음에 그 TLB도 이제 트래쉬만 있잖아요. 트래쉬.
쓰레기만.
네, 근데 그때 이제 하나 얻었을 때 이제 스페이셜 로컬티 보장하기 위해서 옆에 그 인근에 있는 그 페이지 테이블과 같이
아니야, 그건 아니고
네,
요청한 엔트리만
네,
그 엔트리만 시작했으면 왜냐하면 이게 4kB에 대한 정보이기 때문에 4kB 정보 때문에 인스트럭션 패치를 하면 명령을 넣고 0번지, 4번지, 8번지 이렇게 계속 증가를 하잖아요.
네,
그럼 첫 번째 명령 바꿀 때는 미스가 나지만 두 번째 명령은 그래서 갖고 오는 거죠.
엔트리 자체를
요청한 엔트리를 갖고 오는 거지. 두 번째 인스트럭션 4번지를 할 때는 얘가 갖고 있잖아. 그 트랜스. 그러니까 이미 그 좋은 로컬리티를 보여줄 수 하나만 있고 다른 페이지는 어쩔 줄 모르는데 미리 갖고 올 우리 캐시하고 좀 다르게
네,
얘는 요 자체만 갖고 와도 이 자체가 4kB의 정보이기 때문에 굉장히 좀 많이 커버를 하잖아요.
그럼 그 캐시랑 그냥 다른 그런 거는 안 하고 그냥 이 한 엔트리만
요청한 엔트리만.